So the whole purpose of this is to apply our knowledge of Newton's universal law of gravitation, which we learned in the previous unit, with circular motion so we can analyze motion of satellites that are traveling in circular orbits. Most natural satellites are not perfectly circular in their orbital path. They are what's called elliptical. There's this thing in mathematics called eccentricity, and the more eccentric the orbit is, the more elongated it is. When you start looking at satellites in orbit around the Earth, or say the Earth in orbit around the Sun, or the Moon in orbit around the Earth, their eccentricity is extremely tiny, which means they are elliptical, but they're so close to being a circle that nobody cares. If we treat them as a circle, if we apply the physics of circular motion to them, even though they're not circular orbits, it works out very close to being 100% correct. You get my drift here? Okay. So let's take a look at a question. Isaac Newton recognized that objects with mass will accelerate towards the Earth due to the force of gravity between the mass and the Earth. So he visualized the moon, and he said the reason why the moon is traveling around the Earth is it's falling towards the Earth. The moon is falling towards the Earth. The moon is in free fall. There's no other force acting on it other than the force of gravity. So it must be in free fall. Why doesn't it strike the Earth? Well, we're going to learn about that right now. If the moon is accelerating to the Earth but never reached the Earth, maybe it's because it's moving with such a path that the distance it falls matches how much the Earth curves downward away from its motion. And this is a thought experiment that he had. He visualized the moon as falling towards the Earth but falling around the Earth. It's a pretty weird thing to visualize. So I have an animation we're going to look at. This is called Newton's cannon. And it's just a thought experiment. That is meant to be a diagram of the Earth. They knew what the continents looked like. This is just some graphic that somebody's come up with to make it look old, I suppose. And there's a mountain, and that mountain is very clearly too big. It's not drawn to scale, right? But we're stretching our imagination already, because what Newton has imagined we're doing is we're going to fire a cannonball from the top of that mountain towards the right. So if we fire it, and I want to get a little bit of sound to this, although it might screw up my recording. We'll see what happens here. No, we're okay. If I fire this, it hits the ground, right? Pretty cheesy sounds, pretty cheesy animation, but you get my drift. What if I fire it with a greater speed? That is a speed of about 4,000 meters per second. And, keep in mind, there's no mountain that tall on Earth, okay? So the numbers we get here are not going to be perfect. What the question is asking us to do is find the speed that will result in a circular orbit. So that's not working. I'm going to increase this to maybe, it doesn't matter, 5,800 meters per second. And it fell further away than it did before. You might go, well, okay, then let's do this. Let's increase it to over 14 kilometers per second. Bye-bye. It's not going to come back, right? It's too fast. It's greater than what we would refer to as the escape velocity of Earth, which I don't like because it's not of Earth. It's the escape velocity of objects from Earth, but that's okay. What if we go to, I'm going to go to 6,600. It hits. It doesn't go all the way around. What if we go to, I know what we're after here, but I'm going to go to 7,000. It hits. What if we go to 7,700? It's It's getting further away from the surface of the Earth, isn't it? But now it's getting closer to the surface of the Earth.
Ow.
Hit the person on the back of the head. And the reason why that happened, even though it was getting further away, so if you want to call the distance a radius, which it isn't, the reason it's getting further away, I don't want to say that. The reason why it returns back to where it came from is even though it's getting further away, when it's further away, there's less of a force of gravity, so its centripetal acceleration, if you can call it that, is less and it slows down. And then it speeds up. This is an elliptical orbit, and we have many satellites around Earth that are in elliptical orbits. We are after a circular orbit. So I'm going to slow it down a bit more. Let's try. Okay, come on. There we go. 7,300. I'm going to do that one again with all of the, I don't know why we didn't hear the person say, oh. I'm going to do it without all the tracks. I think it gets a little bit closer to the Earth and then a little bit further away again. So if I had to, there it is. If I had to guess, we could say 7,300, 7,400, 7,200. You get the basic idea here. Okay. So let's go back to our handout. Use the link below to answer the following. What speed for a cannonball results in a fairly circular orbit? Well, you know, I think if you went anywhere from about 7,200 to perhaps 7,400 meters per second, it's going to be fairly circular. There's no sense in us trying to pinpoint it down to a more precise value because this orbit is based on a mountain that is maybe altitude above the surface of the Earth of 1,000 kilometers or something. It's just a ridiculous diagram, okay? But the point is there is some particular speed that will result in a circular orbit. What two possible things can happen if the speed is greater than the speed found? So if the speed is too small, it hits the Earth. If the speed is too great, it could still result in an orbit, what we call a stable orbit, but it will be elliptical. So it could be that if you go beyond this speed, you get an elliptical orbit. Or the object never returns. And we saw both of those, right? Just to show that to you again. Did I close that? I didn't think I did. Well, there they all are. So that's too small. This is too big. It's not an orbit. It's not even an orbit, this one. But if you go to maybe around, I'll go 8,900, I'm guessing it's going to come back. We just have to be patient. I think it's going to come back. I don't know. You want to put money on it? I might lose my money. See, the orbital period of Halley's Comet is like 80-some years. So, because as it goes further away, it really slows down. There it is. Oh, you were... It's good that noise was there in case you look away. So that would be an elliptical orbit, right? That's not going to be circular. It goes way down. I don't know if we trace this. I'm guessing it would be below the floor at its lowest point from your vantage point. Okay. All right. So when a satellite is in circular orbit, the net force acting on it is caused by gravity. It's caused by a gravitational force of attraction between the satellite and the planet that it is orbiting. This net unbalanced force is the force of gravity, and we can call it the centripetal force if we like, because once again, what is the relationship between net force and centripetal force? They're the same thing, right? As long as the object's moving in a circle. This is it. This is the key to solving any satellite problem. So if I give you this information that we have an Earth-based satellite with an orbital radius of 9.4 times 10 to the 7 meters, I probably don't need to say from Earth. That grammar is incorrect. If the orbital radius is that number, it's the orbital radius. We don't say orbital radius from Earth, but I can clean that up later in my note package. So your starting point for satellites is always to say, well, the net force is the force of gravity. Because if this is the Earth, and this is the satellite, there is but only one force acting on the satellite. It's the force of gravitational attraction between the satellite and the Earth. That's the only force acting on it. Unless there are, little thrusters that are being fired every now and then to stabilize its orbit, which I'll talk about in a minute. So the net force is the force of gravity. Could I say this? Sure. Do I need to? No. But I could. So what is this? This is MA, and A is centripetal. Let me ask you a question here. What is accelerating, the satellite or the Earth? Not a trick question. What's experiencing the circular motion? The satellite. So it's important for you to understand that the mass on the left is the satellite mass. Okay. Whereas over here, when we go G mm over r squared, one of those masses is the satellite and one is the Earth. And I like to use lowercase m for the object in orbit. So this G mm over r squared is from Unit 2. I like to use the lowercase m for the satellite, and that means it cancels, which brings up an interesting point. The mass of the satellite has nothing to do with its motion. Now, what are we asked to find? How fast is the satellite in its free fall orbit? By the way, when you look at video of astronauts inside of a space station that's in orbit, the reason they are weightless is they're falling. It's just that the satellite or the thing they're in is falling as well. So they're in a continual free fall around the Earth. We're going to change this acceleration to v squared over r. And we're just going to follow what the math tells us to do. To be honest with you, the physics is done as soon as we finish writing that. That's the physics. We're applying Newton's second law. We put in some different ways to calculate forces. So I'm going to multiply both sides by r and get v squared equals g times the mass of the Earth times r over r squared, which gives us v equals the square root of g m over r. And that square root extends over all of gm over r. You've got r to the 1 on the top of this expression, and you have over r squared, so that cancels. If you like, I'll put v squared equals gm over r before we get to this thing. I think most of you are capable of just going from the v squared equals gmr over r squared to that. The physics is done. It's the matter now of putting the numbers in the calculator. In fact, I don't even feel like writing the numbers down. If you need the benefit of seeing the numbers written down, that's fine. If you are doing an assignment and I ask you to show the work, you put those numbers in. Sam, do you have a question? No, and that's why, you know, I think what happened is I originally had this question saying with a distance of something from the Earth, and then I thought, well, let's not do that. Let's just call it a radius. So as soon as you see radius, that's r. What Sam's asking, in case you didn't hear it, is, do we have to add the radius of the Earth? And the answer is no, because this is not an altitude above the surface of the Earth. And this is my fault. These last couple of words seem to imply that it might be, but that wasn't my intention. It says the radius is this. We'll look at one example today where we do have to do that. So it's just a matter now of going to my formula sheet, seeing that capital G is 6.67 times 10 to the negative 11, but I suspect almost all of you remember that, times the mass of the Earth, which we've used so often that you probably remember that as well, divided by the orbital radius. This is not the radius of the planet, it's the orbital radius. It's the radius of the circle that the thing is traveling in. And then I have to take the square root. (2,058 meters per second). I want to, and I know I have a hard time doing this, but I want to avoid a lot of extra discussions here today. Briefly, and I could talk a lot about this, but we will when we have more time. Briefly, since the mass of the satellite doesn't matter, then at that orbital radius, you could have, so here's the Earth, and then we have an orbital radius of 9.4 times 10 to the 7, which is about 10 times the radius of the Earth. No. Yeah, it's about 10 times the radius of the Earth, because the radius of the Earth is 6.37 times 10 to the 6, and this is 9.4 times 10 to the 7. It's quite a large radius. So here's the Earth, and then we also have this satellite. 1, 2, 3, 4, 5, 6. So let's just say that's the satellite's orbit. Okay. But because the mass of the satellite doesn't matter, you can have a satellite with that orbital radius right next to another satellite with that orbital radius. You could have a whole ring of satellites almost touching each other, and they're all going to be moving at the same speed. I think just intuitively you understand that if we had a lower orbital radius, it would be traveling faster. Because it's closer to the Earth, there's more gravitational force affecting its motion. Let's take a look at the next one. And again, I should have taken time and retyped these. My intention here is that's the orbital radius. Okay? And I will tell you right now that that distance is so big, even if it's the distance from surface to surface, the orbital radii of the Earth and Moon don't matter. Not the orbital radii, the radius of those two objects doesn't matter. So this, my intention here is for you to say r equals 3.844 times 10 to the 5 kilometers, which is 10 to the 8 meters. So I just want to clear that up, and that's my mistake. I should have been more clear in my language here. That is, in fact, the radius of the Moon's orbit. The question is, what's the orbital speed? Well, that's easy. And you're going to get maybe a little annoyed with me here, but I'm a big boy, I can take it. You need to write this, then you need to say MA equals G MM over R squared. Then you need to say this is centripetal, which leads you to mv squared over r equals G mm over r squared, which means you can cancel the m's, and v is the square root of G, mass of the planet, over r. I suspect after doing two, maybe even one, but two or three of these, you know that this bottom equation is how you find the speed. But by the time you get to physics 30, you might have 6 or 7 or 8 different results, more than that, of the equation you use, and you cannot set out to memorize things. I've said it before, I'll say it again. Students who are successful in high school physics are successful because they understand the physics principle. And they apply the physics principle. Those students who try to just memorize formulas are not successful. Look at what we just finished doing with circular motion and vertical motion. If you try to memorize that and memorize elevators and memorize inclined planes, you won't. So, let's calculate that. This is above Earth, isn't it? Oh, it's the moon. Of course it's above the Earth. So let's do a calculation again. The square root of Newton's universal constant of gravity times the mass of the Earth divided by the orbital radius of the satellite. The moon is a satellite around Earth. It's just a natural satellite. So there's my G, my mass of the Earth, divided by the radius. I think in the previous question I might have calculated that first and then taken the square root. I'm just taking the square root here in one shot. And we get 1,017.8 meters per second. And then the next question says, what's the orbital period of the moon? How long does it take? Now, I have a certain way that I think is best to solve this problem. And it's even though you may not be asked to find the speed, when you're asked to find the orbital period, find the speed first. Okay? Why is that helpful? Because of that. We know this speed is a centripetal speed, and we know that it's equal to 2 pi r over t. So all we have to do is put the speed into that formula and find the period. Okay. So I'm going to take 2 times pi times the radius of 3.844 times 10 to the 8. Can you just confirm that I've remembered that correctly? And then I'm going to divide by my speed, which is my answer, and I get this number. And that's a number of seconds. And if you wanted to, you could certainly say 2.37 times 10 to the 6 seconds. You could. But let's figure out what that is in a more reasonable unit of time. Let's divide it by 60 to get minutes. Let's divide it by 60 again to get hours. And let's divide it by 24 to get days. Oh, 27 days. The length of a lunar month. Right? The moon goes through its phases approximately once every month. It doesn't match up perfectly because we've devised calendars of 28 days and 30 days and sometimes 29 days. But the lunar month is 27 and a half days long. That's how long it takes the moon to make one complete orbit around the Earth. Any questions with that example? All right. This diagram, I pulled this from your textbook. This is laughable in its scale, right? This is saying that orbital altitude is 912 kilometers. The distance from coast to coast across Canada depends on where you're measuring from, but it's about 5,000 kilometers. And you can see that from Victoria to Halifax, I'm saying is about 5,000 kilometers, and yet they're saying that distance above the Earth is 912 kilometers. That 912 kilometers, this is a very low altitude satellite. It's very, very close to the surface of the Earth. And it's what we call a polar orbit, that the Earth is spinning this way, and the satellite is going around it this way. And it's called the Landsat satellite, and it takes continual pictures and makes measurements of what it's seeing on the ground. And the nice thing is if it keeps orbiting this way and the planet is rotating, it's cutting through a different swath of the planet every time it comes around. Right? So it might come around over Idaho. I don't know if that's where Idaho is, but it might come around downwards over Idaho, and then the next time it comes, this whole planet will have been rotated a bit, so it's going to come down across North Dakota. I don't know. Okay. So what is its orbital speed and period? Even though I just told you that you have to know where this comes from, I hope you're okay with, in the course of this lesson, me just saying, let's just write it down. You have to be able to derive it. So, Sam, what are we going to do to find the radius that goes in here? Like, is this 912,000 meters the orbital radius? Right, I have to add the radius of the Earth. So this R will be 6.37 times 10 to the 6 plus 9.12, well, I won't do that, plus 912,000. These are both meters. I mean, just while I've got these numbers here, that 912 kilometers is only about 14% the radius of the Earth. So I'm just doing that to give you a scale to what's really going on here. We do have to add these, though, to get the total orbital radius, or the orbital radius. Do you get that for the sum? How many of you would just put it all in one shot and put brackets around the two distances? Okay. I'll do that then. If you want to just use this one, you can. Square root of g times the mass of the Earth divided by, in brackets, the radius of the Earth plus that 912,000. There's a temptation, by the way, here to square that r, because you get so used to squaring it. But it's not r squared in the formula. I'll double check my entry. Oh. Forgot to put the exponent part for the mass of the Earth. And, oh, I got the 0 there. I think it's okay. Are you getting 7394 meters per second? Or 7.4 kilometers per second. I'm not doing the 3.6 thing. I'm just going meters per second to kilometers per second. I'm just dividing by 1,000. What is the period? Well, the period is found using V equals 2 pi r over t. And again, this is a low orbit, or low altitude satellite. It's moving very fast. Not like the moon that's taking a loping 28 days to go all the way around. 2 times pi times the radius, I'm just going to use this, divided by the speed. I get 6187 seconds. Yes? About 100 minutes. About an hour and 40 minutes. Roughly. So in that hour and 40 minutes, let's call it an hour just for now. In that 1 hour that it goes around, the Earth will have rotated 1/24th of a rotation, because it rotates once every 24 hours. And then it's going to be covering different information continually. Any questions, sir? Sam?
Do you care if you put it in hours or minutes?
No, but you should understand that I could ask the question on an exam and say the number of hours rounded to the nearest tenth. And you should understand that when you solve these problems, you always use standard units, so you'll get seconds. And then if you need to convert it, you can. Or similarly, Sam, if I had a multiple choice question and all of the numbers were in minutes, then you'd have to convert your answer to minutes. But as an open-ended thing, it doesn't matter. Any other questions with this one? All right, there's a special type of satellite we would like to talk about here called a geostationary satellite. And I had a globe in my room, and I see that somebody's borrowed it, so I can't show this to you. But a geostationary, and sometimes it's called a geosynchronous satellite, is a satellite that is always above the same point on the Earth's surface. And it's always in what we call an equatorial orbit. It's always in orbit above the equator. The equator, of course, is that line that is a circle dividing the northern hemisphere from the southern hemisphere in terms of the Earth's rotation. So if my head is the Earth and this is the equator, the idea behind a geostationary satellite is that there's an altitude above the surface of the Earth, above the equator. This is my version of globe. And as the Earth spins, this is in orbit. But if this satellite is orbiting once every 24 hours, it will always be above the same point on the surface of the Earth. Because it takes 24 hours for the Earth to rotate once. If the orbital period of the satellite is 26 hours, then they're not going to be synced up all the time. So the idea here is that the orbital period of a geosynchronous satellite is 24 hours. Why do we have geosynchronous satellites? And by the way, we've got hundreds of them up there. And because they're all going to be at the same altitude, they're all moving at the same speed. So there's this ring of satellites up there at that interesting altitude where they always are moving over the same part of the Earth. They're always above the same part of the Earth. Why would we want that? Well, when I had an acreage, we had a satellite dish. And if we wanted to watch something, I didn't tell my roommate to go out there and just keep moving the satellite dish and follow that satellite, right? We install the satellite dish, we align it, we get the strongest signal, and it's pointing at the satellite, and the microwave radiation from the satellite is bouncing on that dish and being collected. It's microwave radiation. It's not very intense, but it's microwave. Same as your cell phone. Your cell phone uses microwave radiation. So communication. is one of the reasons. It can also be used for nefarious purposes or good purposes, depends on how you look at it. I don't mean spying like spying on your neighbor, but I'd be willing to bet that there's a satellite that's in such a position above the surface of the Earth that is continually watching what's going on at the Kremlin. I would have to believe that the United States of America has a satellite looking at what's going on in different places in Russia. I would have to believe that Russia has satellites above certain places in North America. China, the same thing. There's this continual stupid thing that goes on in our world of all of these wars and spying, and people want to be superior and governments want to be better than other governments. It's absolutely ridiculous, but it's a fact. I could put other things there. GPS is one. I mean, GPS satellites, they're the satellites that if you are using your mapping app on your phone, it's what's continually pinging off of the satellites in your phone. But there's so many GPS satellites out there, you know, it's not that you have to aim your satellite or your phone at a satellite, right? There's enough of them continually, this is a weird thing, enough of those satellites continually sending radiation down on the Earth so that no matter where you are, you get hit by it. It's not harmful. I'm just saying it's there. So there are other reasons as well. At what altitude must we put the satellite in order to get a geosynchronous satellite? So if we start off with FG equals FNet, and we go M times V squared over R, well, I better not do that. We go M times A equals G M M over R squared. We're trying to find R, correct? So that, by the way, we can subtract the radius of the Earth to get the altitude. And you might be a little annoyed at me with this because I'm going to do all this and I'm going to say it doesn't help. Because your next step is to say, well, that means that, might as well kill these guys. Your next step is to say that G M of the Earth over R squared equals V squared over R, and T is not in there. Or sorry, yeah, T is not in there. We know T, right? We know the orbital period is 24 hours, but it's not there. So you might think, well, let's calculate the speed so that we can find the radius. That would be a logical thing, except we can't find the speed because we don't know the radius. You're with me on that? So the solution is to put in the other form for the centripetal acceleration. Right? Centripetal acceleration is V squared over R, but it's also that thing. And the math now gets not, clunky is the wrong word, it gets more complicated. Because when we did this by putting in V squared over R, one of your R's canceled. Here, the R's don't cancel. You end up with an R cubed when you cross multiply. So this AC is V squared over R, or 4 pi squared R over T squared. And in this type of question, you have to use the 4 pi squared R over T squared. So if we cross multiply, we get GMT squared equals 4 pi squared R cubed. But once again, everybody, This is the physics. At this point in time, it's just a matter of math and putting numbers in. I prefer, and I think it's a good idea for you as well, to solve first. And then put the numbers in. And as you probably noticed throughout this whole lesson, I'm not even writing down all these numbers. We know what they are, and we can see them when we put them into our calculator. Why would we waste time writing them down? Just a quick question. Am I going too slow today? Okay. Am I going too fast? It's Goldilocks then, right? It's just right. Okay. We're probably going to spend a second day on this. Okay. And we'll shave off time elsewhere in the course. So I need to calculate what this is. And then take the cube root. So 6.67 multiplied by 10 to the negative 11. I need to multiply that by the mass of the Earth. I need to multiply that by, well, just, I guess, we need to know what that is in seconds. So you need to multiply it by 60 to get it into minutes, and then you need to multiply it by 60 to get 86,400. Okay. Very closely connected to Sam's question when he asked, do we have to convert to a certain unit after we get an answer? And I said, no, but we have to use standard units when we do the calculations. So we have to use seconds here, because everything else is in standard units. So I've entered capital G times the mass of the Earth times the 86,400 squared. I just don't want you to make a... Yeah.
You have 5.98.
Oh. You know why, right? Because that's what the mass of the Earth was on a formula sheet some other point in time. It's just hard to break old habits. 5.97. Thank you, Sam. I just want to enter something, and I want you to look carefully at what I'm entering and tell me why I'm wrong.
Because now you're multiplying by pi squared.
Right. So when I say divided by 4 pi squared, I'm saying divided by 4 times pi squared. But my calculator doesn't know I mean divide by 4 pi squared. It's going to divide by 4 and multiply by pi squared. So what most of you will want to do is this. Okay? And you can feel free to do that. What I do, just because I'm a product of my education, is I do this. That just means I've learned to do things a certain way. If I have to divide by 4 pi squared, that means I have to divide by 4 and divide by pi squared. When I hit equals, I get this number, but that is not r. I need to take the cube root of r. Now, on your TI calculators, cube root is found by going to your math menu and scrolling down until you see it. And then we can put the answer in there. You can feel free instead, if you've completed Math 20, where you're taught that a cube root is the same as raising to the exponent of 1/3, you can do that. Anyway, this is the orbital radius, and I'm getting a psychic vibration here that the bell's about to ring, based on the rustling. What do we have to do to that to get the altitude above the surface of the Earth? Right, take the radius of the Earth away from that. So I'm not going to worry about writing that down. We'll start tomorrow by just finishing off this problem. And I know it was a long lesson, but you start with FG equals F net for satellites. No homework. Well, I'll do it tomorrow in an empty room. No, I'll do it Monday. Okay, so have a great weekend. We'll review this on Monday and get some practice Monday.